Hello, and today we're going through further vectors for further maths for the whole of the topic for year 1, not year 2 because that goes into lines and planes. So let's get started with the vector equation of a line, which has a format like this. R is equal to A plus lambda D, where R, A, and D are all vectors, where R is the position vector of any point that you're trying to find on the line. A is a position vector of any point of the line, and D is the direction vector of the line. And if we were to draw how this looks like, we would draw a line like this, and say the origin is over here. Our position vector to a point R, where we're trying to find, would look something like this. R to a point R over here. Say we have any other point A over here. A position vector between these two will look something like this, and we'll call it A. So to find the value of this R, we would need to add this vector plus another vector that gets up to it. And if we look at the equation, we have A plus the other vector, which is lambda D, where our D, so lambda is a scalar, so it's just a number, and D is a vector, and this D can be shown by just a direction vector to show which direction the line goes. And if you multiply this by any number, you can get any point on the line. So to find your position vector, you can just find it as the sum of two other vectors, which is a vector that takes you to the line, which is the position vector of any point on the line, and then another vector that takes you along the line, which is a multiple of your value of the direction vector. So the direction vector goes along the line, and the direction vector can go either way, so negative direction or in the positive direction. So you could flip the signs, and to get, say, points over here, you could flip the arrow and you could get points on this side as well. And you can just do negative values of lambda to go the other way as well. So now let's move on to a question where they're asking whether this line and this line are both describe the same straight line. So as you can see, these two are in the same format as here. So R is equal to A, which is a vector here, times a lambda times a direction vector here and here. So to prove that they're the same straight line, we have to prove that the line is, first of all, that they're parallel and that the two lines intersect. Because if they're parallel and they intersect, there would have to be two straight lines which are exactly the same, because they intersect at a point and they're both parallel. So first, how do we check that they intersect? We can look at their position vectors, and if they're both the same, we can just say that they both have a point on the line which is the same. So let's look at the position vectors of a point on the line. So the A1 from the formula from before, from this one, our A's are, so our A for this one is 2, 5, minus 3, and our A2 is 2, 5, minus 3. And we can see that both of these are the same. So we can say that they do intersect at one point. So we've covered this part here. Now all we have to do is check that they're parallel. So how do we do that? So now we look at the direction vectors. If the direction vectors are either the same direction but different magnitudes, they are also parallel. So for example, our D1 is equal to 2, 1, minus 5, and our D2 is equal to minus 4, minus 2, 10. And if we take out a scalar from this, we can get, so simplify this, we can get minus 2, 2, 1, minus 5, and we can realize that this, so D2 is a multiple of minus 2 of D1, because 2, 1, minus 5 is the same for both of them. So we can prove that these two are parallel. So because they're both parallel and they both intersect, that means they are the same line. So the answer to this question is yes, they are the same line. Now let's move on to another question. So the question is asking to find the vector equation of a line connecting these 2 points. So if we draw it, we would have point A, for example, over here, with 2, 1, 3, and point B over here, for example, with 3 minus 1, 5. And if you make a line between these two, you're going to get something like this. So remember, the equation of a line has the components of a position vector of any point on the line and the direction vector of the line. So we can write this out. So to find the equation of the line, we will need to find A and D. So our A can be a position vector of any point of the line. So because we have 2 points on the line, we get to choose. We can choose either this one or this one. So I'm going to choose A. So our value for A is going to be 2, 1, 3, which is our position vector of A on the line. And for our direction vector, we can just use the distance between the two. So the direction vector between the two, which is just AB, which we can write as OB minus OA. And this is equal to 3 minus 1, 5, which is the position vector of B, minus 2, 1, 3, which is the position vector of A. And we get our direction vector of 3 minus 2, which is 1, minus 1 minus 1, which is minus 2, and 5 minus 3, which is 2. So this is equal to our direction vector. So if we just put it back into this equation here, we're going to have R is equal to 2, 1, 3 from over here, plus a lambda, and then our direction vector, which is just 1 minus 2, 2. And this is our vector equation of the line. So this is part A. So now let's move on to part B, where it's asked to find a point C which lies on the line so that the length of AC is 5 times larger than length AB. So because the direction vector looks something like this on the line, and this is our D that we found before over here, we can say that a point C is 5 times the direction vector of that we found before of AB. So that is 5 times the length of AB. So how would we do this? So to find a point on the line, we would just multiply the direction vector times 5. So we'll just substitute our lambda as 5. And we would get R is equal to 2, 1, 3, plus 5, 1 minus 2, 2. And we get a point which is 7 minus 9, 13, which is the position vector of this point C, which is 5 times the length of AB, which is 5 times the distance away from A as B, and the coordinates can be written as 7 minus 9, 13. And we could also have another point where we go in the other direction, which is also 5 times the distance from A as B. But we'll just go in the opposite direction, because in this case, we just multiplied by 5. So we went up the line. So in this case, we're going to go down the line. So we're just going to substitute our lambda as minus 5. So we're going to do R is equal to 2, 1, 3, minus 5, 1 minus 2, 2. And we're going to get minus 3, 11, minus 7 as our position vector. So our other point is going to take the coordinates of minus 3, 11, minus 7. So these are the answers to both of these questions. So now let's move on to Cartesian equation of a line. So for the Cartesian equation in 2D, if we have a direction vector that looks something like this, AB, with components AB in 2D, our gradient of our line in 2D is going to be B over A. And now in 3D, if you have a vector equation of a line which looks something like this, we can write this out as its individual components like this. So X, Y, Z is a R, which is equal to a x, a y, a z, plus lambda dx, dy, dz. And now if we write this out individually, we will get three separate equations, which is x is equal to ax plus lambda dx, y is equal to ay plus lambda dy, and z is equal to az plus lambda dz. And now if we rearrange these equations to find lambda, we're going to get lambda, to make lambda the subject, we'll get lambda is equal to x minus ax over dx. Lambda is equal to y minus ay over dy, and lambda is equal to z minus az over dz. And now if you equate all the lambdas, you can get the equation of the Cartesian equation of the line. So you make x minus ax over dx is equal to y minus ay over dy, which is equal to z minus az over dz. And this is the Cartesian equation of the line. And this is going from the vector equation of the line to the Cartesian equation of the line. But to go backwards, all you have to do is equate each one to lambda, rearrange to get your equations here in terms of x, y, and z, and then substitute it back into the original equation. And then you can leave it as r is equal to your a vector and your direction vector. And this is how you go the other way around. So you can go either way around, from Cartesian to vector or vector to Cartesian. So now let's move on to a question where they're asking for the vector equation of the line from this Cartesian equation of the line. So remember what we said before. So to find the vector equation, we just have to make each one of these equal to lambda. So we're going to say x minus 2 over 6 is equal to lambda, y plus 7 over 3 is equal to lambda, and z over 2 is equal to lambda. And now if we rearrange the equations, we're going to get, to make x, y, and z the subject, we're going to get x is equal to 6 lambda minus plus 2, y is equal to 3 lambda plus 7, and z is equal to 2 lambda. And now if we stack this up in vector form, we're going to get x, y, z is equal to, so the position vectors, we're going to get 2, 7, and then the 0. So that's for the position vector. So I'm going to have 2, 7, 0 plus lambda times the multiples of lambda, which is 6, 3, and 2. So 6, 3, and 2. And this is the vector equation of the line, which we can write finally as r is equal to 2, 7, 0 plus lambda 6, 3, 2. Just make sure to leave it in terms of r like that. And this is the answer to the question. So now let's move on to another question. So this question asks, so it says there's a Cartesian equation of a line where it says this, and then it's a different form to the previous ones, where it has a comma and says z is equal to 7. This means that every point on the line will have a z coordinate of 7. And then it says a point a minus 1 b lies on the line. Find a and b. So because we said before, every point on the line is 7, we have has a z value of 7. We know that b has to be 7. And for the rest, because we know our value for y, we know that 6y, which is minus 1, substitute y as minus 1 over 3 is equal to x minus 6. We can substitute because from this part of the equation, we can substitute our x value as a. If we rearrange this equation, we're going to get minus 6 minus 1 over 3 is equal to a minus 6. This will be minus 7 over 3 is equal to a minus 6. And we can rearrange to get 6 minus 7 over 3, which is equal to A, which is equal to 11 over 3 or 3.6 recurring. And now we found our values for A and B. So the coordinates of the point would just be 11 over 3 minus 1, 7. Now let's move on to intersections of lines. So if you have two lines with the equations R1 is equal to A1 plus lambda D1, and you have the equation R2 is equal to A2 plus lambda D2. To find a point of intersection, you would just do R1 is equal to R2. But not all lines intersect. So in 2D, you either have parallel lines, like this, which don't intersect. But in 3D, you either have parallel lines similar to 2D, and you also have skew lines, which are not parallel and don't intersect. If I were to draw a 3D space like this, skew lines will look something like this. We have one line going this way and another line going somewhere like this. So they're neither parallel because they're not parallel like this, and they don't intersect either because this one goes below it and this one goes above it. So now let's move on to a question where they ask, find the coordinates of an intersection of these two lines, where we have, instead of column vectors, we have our vectors in terms of I, j, and k. So how would we find the intersection? Remember that we make the r of one equation equal to the r of the other. So in this case, the r of this one would be equal to the r of that one. So if we write our equations out in column form to make it easier, we would have r1 is equal to 2 minus 1 minus 1 plus lambda minus 1, 2, 3, and our r2 from r1 from this equation, and this is r2, would be equal to 1, 1, 2 plus mu 1, and because there's no j component, so that will be equal to 0, and then 3. And if we join these two vectors together by doing r1 is equal to r2, we can join the vectors together and make it into one vector. So if we combine this vector here, we're going to get 2 minus lambda by multiplying the lambda up here. Then we're going to get minus 1 plus 2 lambda, and then minus 1 plus 3 lambda. And this we can make it equal to 1 plus lambda, 1 plus lambda times 0, which we can just get rid of. So we just left as 1, and then 2 plus 3 mu. And now if we write these equations out separately, so to find each of lambda and mu, so we'll find each of lambda and mu and then substitute into each of these. And if we get the same value for both of the r's, we've proved that they intersect. If we get different values, that means they don't intersect. So let's find lambda first. So it will be easier to find lambda because there's no mu on this side. So we'll use the middle part of the vector. So the middle component of the vector. So we get minus 1 plus 2 lambda is equal to 1. We'll add 1 on both sides. So we get 2 lambda is equal to 2. So our lambda is equal to 1. If we substitute that into the second equation, so r2 over here, we're going to get a coordinate of r2 is equal to, or we can also substitute in here, so we'll get 2 minus lambda, 2 minus 1, which is 1, minus 1 plus 2 lambda, which is 2 minus 1, which is also 1, and then we're going to get minus 1 plus 1 times 3, which is 3 minus 1, which is 2. And now we have our value for R2, which could possibly be the intersection between the two lines. But now we're going to double check this by finding out what mu is and then substituting into the R1 equation. So to find mu, we do the same thing from here, and we can use either the top equation or the bottom one, it doesn't really matter. So I'll use the top, so 2 minus lambda is equal to 1 plus mu. We know that lambda is equal to 1, so this will simplify as 1 is equal to 1 plus mu. And we know that mu, if we rearrange, take away 1 both sides, we're going to get 0 is equal to mu. And now if we substitute 0 onto this side, we're going to get R1 is just equal to this side. So we're going to say R1 is equal to 1, 1, 2, which is the same as the R2. So therefore they both intersect at 1, 1, 2 is the point of intersection. So just to recap, we used the two equations, this one and this one. Then we equated both of them and then found our lambda, substituted into one of the equations. Then we found a point here, and then we found our mu, and we confirmed that it was the same as the other equation, so therefore they intersect at, last step, they intersect at 1, 1, 2. Now let's move on to the dot product. So say you have two vectors that look something like this, a1, a2, a3, and this carries on. And you have another vector, which we would do the dot product to, of b1, b2, b3, and it carries on as well. So the dot product can be calculated by doing a1 times b1, which is these two top ones, plus a2 times b2, which is these two, plus a3 times b3, which are these two, and it just carries on going. You keep adding the however long the vector is, and this will be equal to your dot product. And the dot product is very useful because there's a formula that relates the angle between two vectors and the dot product. So, and this equation is cos theta, which is the angle between the two vectors, is equal to a. So if you have vectors a and b, over the magnitudes of a multiplied by the magnitude of b. And if the two vectors are perpendicular, a dot b is equal to 0. So now let's move on to questions. So this question is asking for the shortest distance from the point, this point over here, and the line over here in vector form. As you can see, it has the position vector, the lambda, and a direction vector as well. So if we were to draw this out, we would have a line that looks something like this, and a point that looks something like this, which is the 0, 5, 9. And to find the shortest distance, it would look something like this. So the shortest distance would look something like this, and it would be at a right angle from the line. And the line has also a point A, 0, 5, 9, and it also has a direction vector like this, which has a vector of -1, -3, 1. And to describe any point on this line here, so the point here, we can describe it in terms of lambda. Remember, because lambda can, this can describe any point on the line with different values of lambda. So because we don't know what lambda is, we can describe this point in terms of lambda. And we can do this by just using the equation of the line, and then joining it into one vector. So we'll leave it as 1 minus lambda, 1 minus 3 lambda, and 3 plus lambda. And this is the point here in terms of lambda. So to find the shortest distance from the point, we can just find the magnitude of this vector here. So to find this vector, all we'll have to do is to find the vector joining both sides. So we can just remember that AB is equal to OB minus OA, which are the position vectors of this one and this one. So we can just take away the position vector of this point here, take away this to get the vector that joins them both. So do 0, 5, 9, take away this, and we would get, so this vector over here would be lambda minus 1, 3 lambda plus 4, and 6 minus lambda. And now we've found the direction, so the direction vector between these 2 points. If we find this magnitude, we find the shortest distance. But to find this magnitude, we still need to find lambda. So to find lambda, what we need to do is, because we know that this vector goes along the line, so the direction vector goes along the line, and it's at 90 degrees to this vector that we just found in terms of lambda. So we know that the dot product of this and this is going to be equal to 0 because perpendicular vectors have a dot product of 0. So if we apply the dot product to these two, we'll just have -1, -3, 1. And then we dot lambda minus 1, 3 lambda plus 4, 6 minus lambda. We are going to get -1, lambda minus 1, minus 3, 3 lambda plus 4, plus 6 minus lambda is equal to 0, because the dot product is equal to 0. Now, let's expand this out. So all we can do now is just solve for lambda to find the value for lambda. So we can then substitute into the magnitude of this to find the shortest distance. So let's expand this out. We'll get minus lambda plus 1 minus 9 lambda minus 12 plus 6 lambda, 6 minus lambda is equal to 0. And if we collect like terms, so we have the lambdas over here, which add up to make minus 11 lambda. And then we have the constant terms, plus 1, minus 12, plus 6. If we add them up, we're going to get minus 5, and this is equal to 0. If we rearrange this, we're going to get lambda is equal to minus 5 over 11. So now we found a value for lambda. All we have to do is find the magnitude of this vector. Because we now know what lambda is, we just substitute our values here. And to find the magnitude, we'll just do the sum of the squares of each component and then square root it. So if we write that out, it's going to look something like this. And this is equal to 7.1223. And this is our value for the shortest distance. So just to recap, we drew it out. Our first step was that we drew it out. Our second step was to find the vector that connected the two in terms of lambda. Then we found the dot product to find what lambda is. And then once we know what lambda is, we just find the magnitude of that vector. So it's pretty straightforward when you understand the drawing. So now let's move on to another question. So the question tells us that there are two lines in the vector equations here and here, and they tell us that they both intersect. And they're asking us to find acute angle between the two lines in radians. So we have theta, because it's acute angle, is less than pi over 2 radians, which is also 90 degrees. And if we were to draw out the lines, it would look something like this, where this would be the acute angle because it's less than 90 degrees. And this would also be the acute angle over here. And we wouldn't use this angle because this would be the obtuse angle. So remember, we had a equation to find the angle between two vectors, where we can just do the dot product of the vectors to find a cos theta of the angle between the two vectors. But here we're working with lines. But remember, a vector that goes along the line is just the direction vector they give us in the equation. So we can just use the direction vector as the vectors for our dot product equation. So we can call this d1 and d2. So if we make a new formula, this would be cos theta is equal to the dot product d1 dot d2 all over the magnitude of d1 multiplied by the magnitude of d2. And all we have to do is just multiply the values here. And to find a dot product, so first let's rearrange to find what theta is. And we can just rearrange and we're going to get theta is equal to the cos inverse of what we just had above. And if we just plug in the values, we're going to get theta is equal to the cos inverse of the dot product, which is the direction vectors are 1, 5, 3, dot minus 1, 1, 3, the square root of 1 squared plus 5 squared plus 3 squared multiplied by the square root of minus 1 squared plus 1 squared plus 3 squared. And to do the dot product, you just multiply this one and add it to the multiplication of this one and this one and this one and this one. So let's do that. So we'll get 1 times minus 1 plus 5 times 1 plus 3 times 3. So in the end, if we plug this into our calculator, we're going to get 0.8466 radians. This is rounded to 4 significant figures. So now let's move on to the cross product. So the cross product is very useful in 3D when you have two vectors like this, and you're trying to find a third vector which is perpendicular to both of these vectors, like this. So it's perpendicular to this one and this one. And say if this is vector A and this is vector B, this vector, the one that's perpendicular, would be A, cross product B. And to find the cross product, you can use a determinant of a matrix which looks like this. So you have the I, J, K vectors on the side, and then you've got your A1, so your A vector right next to it, and the components are written out like this, and your B vector right next to it, and your components are written out like this. So now you would need to know how to find the determinant. So if you want, I can make a video on how to make a determinant, but I'm just going to go through it assuming that you know how to do this already. So first we will look at this column to try and find the determinant. So first we would choose I, and we would write it out like this. So I multiplied by, because we're looking at I, we would cancel out both sides, and you will have to multiply A2 times B3, take away the A3 times B2. And now because we apply the cofactors like this to the matrix, plus, minus, plus, minus, plus, minus, plus, minus, plus. The next row, let's look at the next row. Because the j lies on the minus, we're going to have to do minus j. So add this on, so minus j. And then we multiply this by whatever's left over. So we have a1 minus a1 times b3 minus a3 times b1. And then finally, we have the last row. Because this is a positive, because of the plus, we can just add it on. So we'll have plus k multiplied by a1 times b2, take away a2 minus b1. And now we can write this out as a column form because this is a vector. I mean, this is a vector already, but we can write it out as column form here, just to make it simpler. And this would be written as a2 b3 minus a3 b2. And now it will be the negative of this one because of this negative here. So we would get a3 b1 take away a1 b3. And for the final row, we would get a1 b2 minus a2 b1. And this is equal to the dot product of a and b. So you could either choose to memorize this, or remember that you can find a determinant like this by writing out the vectors right next to each other, and this would be a lot easier to memorize like this. But then you'll have to do more steps. So you either get to choose to memorize this or to memorize this and then just work out from doing the steps, which isn't too hard, to be honest. This is my preferred method. So now let's move on to a question. A line passes through 3 minus 1, 6, and is perpendicular to the lines with the equations in Cartesian form, this one and this one. And then it says find the Cartesian equation of this line. So all we have to do, because we have two lines that cross each other like this, and we're trying to find another line which is perpendicular like this, because we have lines instead of vectors, we can just use the direction vectors of the lines, this direction vector and this direction vector, which we can call d1 and d2. If we can find a cross product of these two vectors, we can find a direction vector of the third line. We can call it d3. And because they give us a point that passes through that line, we can use that as our value to make a vector equation of a line, and then we'll just convert it into a Cartesian equation of a line. So to find the direction vectors from the Cartesian equations, we can look at the Cartesian equation formula from before. So as you can see here, the direction vector is dx, dy, dz, and it can be rearranged into this form where the dx, dy, and dz are at the bottom of the fractions of the Cartesian form. So let's look back at the question. So as you can see, we can use these as our position vectors and whatever's underneath. So if you rewrite these equations, we're going to have x over 3 is equal to y over 3, which is equal to z minus 1 over 1, which is the same as z minus 1. So our position vector, because this is dx, dy, dz, our direction vector can be written as 3, 3, 1 for this one. And now for the second line, this one over here, we can write it out as 3, and then this one would be 1. So let's write this out as well. We're going to get x plus 1 over 3 is equal to y over 1, which is equal to z minus 1 over 5. So the direction vector would be 3, 1, 5. So if we find a cross product of these two vectors, we can find the direction vector of the third line that we're trying to find. So let's find a cross product. So we can just do from before, I, j, k, and then we have 3, 3, 1, and 3, 1, 5. And the cross product will just be I times 3 times 5, which is 15. So multiply these two together. Minus 1 times 1, which is 1. Minus j. 3 times 5, which is 15, minus 3 times 1, which is 3. So 15 minus 3 plus k. And we have 3 times 1, take away 3 times 3, which is 3, take away 9. And if we write this out, we're going to get a column vector, which looks something like this, where we have 14, 12, minus 6. And this is the direction vector of the line that we're trying to find. And we know the position vector of the point on the line. So that can just be 3 minus 1, 6. So the vector equation of the line is going to be r is equal to 3 minus 1, 6, plus a lambda, 14, 12, minus 6. Because we join these two together. Now to convert it into the Cartesian equation of the line, we're just going to use this equation and make it equal to xyz and make each row equal to lambda. One vector, which is 3 plus 14 lambda minus 1 plus 12 lambda, 6 minus 6 lambda is equal to your x, y, z. From this, we get three equations. We get 3 plus 14 lambda is equal to x, 12 lambda minus 1 is equal to y, and 6 minus 6 lambda is equal to z. And if we rearrange each one to make lambda the subject, we're going to get x minus 3 over 14 is equal to lambda, y plus 1 over 12 is equal to lambda, and z minus 6 over minus 6 is equal to lambda. So now if we equate each one of these equations, because they're all equal to lambda, we can get a final equation which looks something like this. We've got x minus 3 over 14 is equal to y plus 1 over 12, which is equal to, or you can write 6 minus z over 6. And this is your final answer for the Cartesian equation of the third line, which is both perpendicular to both vectors. And that's the end of the video. Thanks for watching. I hope this was useful for you.